Welcome back to this course, and we are still dealing with the relations in our discrete mathematics course. And in the previous lectures, we have seen what is the relation and how they are related to sets, as well as you can see the difference and similarities with the functions. And you have seen 6 different types of relations. And today we are going to see what happens when we combine various properties of the relations, and we are going to examine how we can represent more of these relations in different terms, for example like matrix and other form. Let's go on and see how we can combine these relations first. So there are 2 ways to combine relations, R1 and R2. So when we have these 2 relations R1 and R2, let's say you can combine this via some Boolean operators. Can you recall the Boolean operators? Yes, for example and, or, not. And you can also combine these relations via composition function. So if you recall again the composition part, F composition of G and those stuff we have seen while we talked about functions. Yeah, via these 2 parts we can combine the functions, and the functions that comes out of these operators would be quite different. Let's see how they are combined via Boolean operators. For example, consider 2 relations R1 that is greater than or equal to and R2 that is less than or equal to. So we combine them as follows here, like or greater than or equal to union or less than or equal to. So this equals all numbers greater than or equal to or less than or equal to. So when you have this union operators, you have this or function coming up. So that's all numbers that are greater than and less than. And you have this intersection that is represented by AND operator and Boolean operation. So here again greater than or equal to and less than or equal to, which means that that's all numbers that are equal to. And you have this exclusive OR operator, all numbers greater than or equal to or less than or equal to, but not both. Yeah, that's all numbers not equal to. And again you have this all numbers greater than or equal to that are not also less than or equal to. Again this not operator, that's all numbers strictly greater than. Here again we are having this or less than or equal to with the minus sign or greater than or equal to. So this signifies all numbers less than that are not also greater than, which means that that's all numbers strictly less than. Yeah, so we can see from these examples it's possible that results is an empty set at times, but the main idea is that we are combining the relations via Boolean operator. Combining relations via relational composition. So let R be a relation from A to B and S be a relation from B to C. In that regard, let A is an element of A and B is an element of A and C is an element of C. So we can just recall as small letters or the elements that belong to the set A, and here we talk about the relations again. Let A comma B is an element of R and B comma C is an element of S. So then the composition of R and S consists of the ordered pairs A comma C. So we denote the relation by S composition of R. It's like S dot R, that's S composition of R. And note that S comes first when writing the composition. So if you recall the functions that we have deal with, you know that the properties of composition. Again, let M be the relation is mother of and F be the relation is father of. So what is the M composition of F? So you can think of if A comma B is an element of F, then A is the father of B, and if B comma C is the element of M, then B is the mother of C. So in that case, we have M composition of F denotes the relation maternal grandfather, right? So M composition of F, that is mother's father, maternal grandfather. What is F composition of M? So if A comma B is an element of M, then A is the mother of B, and if B comma C is the element of F, then B is the father of C. Again, recall what is M and what is F. M means is mother of, and F means it gives the relation is father of. Yes, that's how we have M to be A is the mother of B, and for F to be B is the mother of C. So F composition of M denotes the relation parental grandmother, father's mother, that is grandmother, parental grandmother. I hope this doesn't confuse you with the relations. Here you can see it's actually the genealogical relations that has been given here. What is M composition of M? If A comma B is an element of M, then A is the mother of B. Then again, if B comma C is M, then B is the mother of C. So M composition of M denotes the relation maternal grandmother, your mother's mother. And you can think of M and F are not transitive relation. You can also look at and see if what happens if you want to perform the operation of F composition of F. Combining relations via relational composition again, given the relation R composition of R can be denoted by R square, and R square composition of R can be denoted by R composition of R is kind of R cube that you have. So in other words, MQ is your mother's mother, that is M composition of M composition of M. Well, with this we can see how we can apply the matrix to the relations. Let's briefly review this matrix part first. We will only be dealing with 0, 1 matrices for simplicity. So each element in the matrix is either 0 or a 1. For example, it looks like this, the combination of zeros and ones. So these matrices will be used for Boolean operations that we can perform here. So 1 is 0, 1 is true and 0 is false. That's how we go about. So matrix transposition. Given a matrix M, the transposition of M denoted M power T, that's M transpose, is the matrix obtained by switching the columns and rows of M. And again, these basic matrix operations you might have already be familiar with, the transpose of a matrix. Say for example, M equals this 1, 2, 3, 4, 5, 6 with 2 rows and 3 columns. Then you have the M transpose to be 2 column and 3 rows, like 1, 4, 2, 5, 3, 6. Again, if you have this matrix of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, these elements are ordered with 4 rows and 4 columns. If you want to take up their matrices, you can see just switch the columns and rows. So in both cases, in both matrices, what we did is we switched the columns and rows. So initially for this matrix, you can see here the row is 1, 2, 3 and 4, 5, 6 and another row. So these two rows we are converting into columns, right? The whole row has been converted into columns. Likewise, the same thing happens here. For example, the first row has become the first column, the second row has become the second column, the same thing happens. So that's a way to show the matrices transpose. And if you note, when you have a square matrix like this one here, the diagonal elements remains the same. The diagonal elements like 1, 6, 11, 12, 11, 16, 1, 6, 11, 16, they remain the same even when you have a transpose. The square matrix, as we have just seen, yeah, the diagonal elements of the square matrix remains the same. Let's talk about a join of two matrices performs a Boolean OR operation on each relative entries of the matrix. The matrix must be of same size, and the OR operation, as you know, it's denoted by the symbol looks like V. So for example here, when you perform the OR operation, simply you have this matrix form with 1 and 0. As you know, 1 represents true and 0 represents false. So when you do the OR operation, you can see, just take the element individually and see when you put the OR operation. So when you have 0, 1 and 0, what happens in the OR? Yeah, when you have 1 and 0, the output is going to be 1. And again 0 and 1, your output going to be 1. Likewise, you perform OR operations for every element, and finally you come up with this new matrix. Matrix meet. So here a meet of two matrix performs a Boolean AND on each relative entry of the matrix. So matrix must be of same size, and this is denoted by the symbol looks like cap A. Yeah. So same way we are going to perform the AND operation on each and every entry. For example, take this element 1 and 1 equals, you have 1, 0 and 1, that gives you 0. Likewise, you are doing for every entry in the matrix. Well, then let us move on for the Boolean product matrix. A Boolean product of two matrices is similar to matrix multiplication. Yes, you can recall the matrix multiplication where we have this C 1 comma 1 is A11 times B11 plus A12 times B21 plus A13 times B31 plus A14 times B41. So instead of sum of products, it's conjunction and of the disjunctions, that's ANDs and ORs. So C11 is like A11 and B11, or A12 and B21, or A13 and B31, or A14 and B41. So you can denote by the symbols. For example, here is two matrices, and if you want to take the product of this two matrix, the C11, that's what we talk about. C11 should be of this combination, right? So if you try to perform this operation, you will come up with taking the first row and first column of this given matrix, perform the operation. For example, the A11 of this matrix would represents, this is, consider this as A matrix and this is B matrix, and A11 represents this element here and B11 represents this element here. So with this thought, you can see how A, this is A11 and this is A12, this is A13, A14. Likewise, you have B11, then B21, B31, and then again B41. So taking all these things, you can perform the operation and operation of each and every elements there. Yeah, you go ahead and find final value of C11. Likewise, for each and every element, you have to perform this operation of product operation, which is denoted by this symbol here, this one, and then you can come up with this product matrix. Relations using matrix. List the elements of set A and B in particular order. So order doesn't matter, but we will generally use the ascending order for us to understand easily. So create a matrix M sub R equals Mij. So Mij is 1 if A I comma Bj is element of R, and it's 0 if it's not an element of R. So let this be a matrix here. Consider the relation of who is enrolled in which class. Let A, the Alice, Bob, Claire, Dan. Then B is CS101, CS201, CS202. R equals A comma B such that a person A is enrolled in course B. So here it is. You know that how this matrix is formed. You can recall from our previous lectures in which we have Alice has taken CS101, Bob has taken CS201 and 202, Dan has taken the course CS201 and CS202. Of course, Claire did not take any course. So with this table, you can in fact create a matrix based on the given relations, just like this. 1 for the place where a person is taking a course, and 0 for the place where person is not taking a course. So let's talk about what is the advantage of using such representations. In fact, right now we have taken the relations and we have converted that into a matrix form. So why it is, how it is good for, is it really useful? Yeah, this is how the computer views the relations, like in a two-dimensional array. And with this two-dimensional array, it can be easy for us to manipulate things. It's very easy to view relational properties there. So we generally consider the relations on single set. And later on, we will also see how the matrix can be used, and various properties of this matrix can also represent different view of a given relation. That's from one way of viewing the matrix. And of course, when you talk about the linear algebras and other places where you use these matrices for greater benefit, here the benefits, or in other words, here things are restricted because we view what we see here is only the binary relations with respect to the matrix that we have in hand. Yeah, so when we say we are having a single set, a domain and codomain are the same set, and the matrix is square, we restrict to that idea. Let's talk about reflexive relation. So for reflexive relation, you have this less than or equal to, so one which every element is related to itself. So even you can see that here you have a matrix of form M sub less than or equal to, where you can see this matrix with a square matrix with 5 cross 5 rows and 5 columns, and you can see the diagonal elements are same. The diagonal elements are same, that is 1 1 1 1 1. So when if the diagonal elements are same, this gives us an idea that this is having a reflexive property. If a center or the main diagonal is once, a relation is reflexive. That is one of the shortcut for us to understand when a matrix is represented here of this form. Irreflexive, and let us consider this part, relation is less than relation, the one which every element is not related to itself. So you have the set of A equals 1 2 3 4 5, and the matrix here is of the form, and again you can note that the diagonal elements here having all zeros. So if center or main diagonal is all zeros, a relation is irreflexive. That is the idea here. Well, moving ahead of symmetric relation, as you recall the symmetric relation of R, the one which if A is related to B and B is related to A for all A comma B. So let A is equal to 1 2 3 4 5, then we have this form of matrix, and again if you look closely into this matrix, you can see the so called the upper triangle. If for every value it is the equal to the value in its transposed position. So when you have the transposition of this matrix, you have some similarities. So this represents the symmetric relation. Why don't you try? Just try to take out all the columns or all the columns and switch into rows. Yeah, when you do that, you will find that you have this transposition of a matrix. Yes, for every value it is equal to the value in its transposition. That is why this relation is asymmetric. Asymmetric is less than one which A is related to B and B is not related to A. So again, looking at this part, you can see here again when you closely examine this matrix, you will find that if for every value, the value in its transposed position, if they are not both 1. So here you can see here these upper and lower triangle, they are ones and zeros, and in this part definitely when you have a transposition, it would not be the same. The transposed matrix would be different, completely different. Just imagine, like if you take a column and if you put that as a switch it to a row, it's not going to reflect the original matrix. They are not going to be equal, and that's an asymmetric property. Coming to this asymmetric relation must be irreflexive. That's one of the goals, which means that the diagonal elements are zeros. Yeah, that's a hint that you have here. Right. Let's go for antisymmetric. So here antisymmetrics, for every matrix that you come up with this relation of less than or equal to one which A is related to B and B is not related to A unless A is equal to B for all A comma B. For the given matrix here again, you can see everything looks the same as an asymmetric property, except that the diagonals here have both, it can have both ones and zeros. Yes, for every value, the value in its transposed position, if they are not both 1, then the relation is antisymmetric. So you can see it's not really a if you take the transposed position of this matrix, they are not going to be equal. So that's kind of an asymmetric property, but the diagonal elements, it can have both ones and zeros. So in this example you have all ones there. Transitivity or transitive property is less than or equal to one which A is related to B and B is related to C, then A is related to C for all A comma B. B comma C and A comma C. So for this property, here again you have this relation. So this again looks like for example anti-symmetry, right? Yeah. So for all the upper triangle we have 1. If for, you can check for every spot A comma B and B comma C that each have A1, there is a A1 at AC, A comma C, then the relation is transitive. So you can see the properties there, the elements, each and every elements. Whenever you have a 1, you also should have, if you have a 1 at A comma B and B comma C, then you should have a 1 at A comma C. That's the idea here. So it's like looking at a matrix. So this matrix doesn't really shows the relations properly, unlike other properties. So let's see further on this and see how the combining relation via Boolean operators can work on. So here is two matrices of expressing the sets for R and S, the relations. And you know, when you join that or R union S, in other words, you are having the OR operator there among these two matrices, it reveals to be the output of this matrix is coming. That's the joining, and meeting is using AND operation, or it's like an intersection. Yes, AND operation of the given matrix. Moreover, you have this multiplication of these two matrices is given here. But why is that this case? So we have the multiplication of a matrix R and a matrix, matrix M sub R and matrix M sub S. So yeah, so which C11 can be taken from both those rows and columns of the given matrix. So we have seen an example earlier on how to do the matrix multiplication. The same idea, going one by one at a time. It's good that today we talked about further on the relations, especially with respect of combining using the Boolean operators. And now you can see even a matrix can express a relation. Most of the relations can easily be understood while viewing the matrix. So still we are in this part of relations. As we continue, we will examine more on this relational properties in the coming lectures as well. So until I see you in the next lecture, have a good time and goodbye.